Took a little while, sorry.
You got to do that every time, unfortunately.
Yeah.
But that's okay. So what do we got tonight? Do we got stuff you can verbalize, or do you need to send me anything?
I think I could probably verbalize it.
All right, go ahead. What
All
kind of
right.
stuff are we doing tonight?
What?
What kind of stuff are we doing tonight?
I mean, the name is escaping me right now. Oh, here, polynomial and rational functions.
Okay. All right. What do we got?
All right, so I was just wondering if we could go through all of this, if that's okay.
Sure.
All right. So in exercises, okay, sketch the graph of the rational function by hand. As sketching aids, check for intercepts, vertical asymptotes, and slant asymptotes.
Okay. Give me the function.
2x squared plus 1 over x.
All right. There are three things that you have to pay attention to when you have rational quotient functions like this. And that is the highest degree of the variable in the numerator and the highest degree of the variable in the denominator. Okay? Let's cover a couple of easy ones first. If I had the following, what's the horizontal asymptote on the bottom equation? The bottom.
Yes.
3/2, right. Because the highest degree is the same in the numerator as it is the denominator, therefore the horizontal asymptote is that.
If it's like, wait, for example, say you have like 3x squared plus 1 over like 2x to the third over plus 2x
If the
squared.
bottom is higher, no matter how many degrees higher, like what you just said, then the horizontal asymptote is always y equals 0. In the first case, where that was a 2, the horizontal asymptote was y equals 3/2. Okay? So those are the two main situations you're going to run into, where the numerator and denominator are either equal or the denominator is bigger. This situation is the third one. When you have the numerator exactly 1 degree higher than the denominator, then you actually do the division. And whatever the linear function that you come up with is, that is a slant asymptote. Well, what's this equal to? That's equal to 2x plus 1 over x, right?
Mm-hmm.
I don't care about this, but I do care about this. That is the equation of the slant asymptote. So if I want to graph that, very first thing I'm going to do is draw the equation of that line. And it's always only this part, never the remainder. In other words, a lot of times you'll have to do these by long division. And you divide the denominator into the numerator. And since the numerator is exactly 1 degree higher, you're always going to end up with a linear part and sometimes a remainder, sometimes not. Okay? It's the linear part that represents your slant asymptote.
Okay.
Now, I still have some restrictions on that regarding vertical asymptote. Where do I have a vertical asymptote?
I'm not sure.
It's whatever makes the denominator 0 and cannot be factored out. Well, I cannot factor out an x from the top. So I cannot get rid of that x in the denominator. So I've got a vertical asymptote at x equals 0. Okay. Now, what that gives me is that grid right there. I've got a horizontal asymptote, I got a vertical asymptote. I don't have a horizontal asymptote, I'm sorry, I have a slant asymptote, or these are called oblique asymptotes. They're always straight lines if you have one. Now, the nature of this function is hyperbolic. You know what I mean by hyperbolic?
Yep.
Y equals 1 over x is your basic hyperbolic function. Looks like that. Okay? So this is hyperbolic in function, which means that either the curve's going to look like this, or the curve might be in the wrong quadrants and it might look like the green. But in either case, it's going to be asymptotic to both of those asymptotes. Okay, you with me?
Yeah.
Now, the question is, which one? Well, that's not always a super easy thing to determine, because I don't know where this point is right here. So I could pick an x value of, say, 3, and my function value should be 6 1/3, right?
Uh-huh.
Well, does that tell me whether it's the green or the red? Not really. However, what's the main difference between the green and the red? The green has x intercepts. The red has none.
So would you just
I would
y
set this thing equal to 0 and see if I can come up with a solution.
would you multiply it all by x?
Well, here's the thing. If I go back and look at this thing before I factored it, let's look at the original, because it's a little easier to see. If I try setting that equal to 0, first of all, if I tell you that a over b equals 0, there's only one way that's equal to 0, and that's if a is equal to 0. Okay? Right? And it doesn't matter what b is. If I give you a rational function, it's only equal to 0 if its numerator is equal to 0. So for this function to be equal to 0, the numerator has to be able to be equal to 0. The 2x squared plus 1, can that ever be 0? No. You got a positive number plus another positive number. There is no value of x that will ever make that numerator equal to 0, which means y can never be 0, which means the green line can't be, because the green line indicates that I have 2 x-intercepts. Well, clearly in this case I don't have any, and so our answer is the red line.
Okay.
And usually you end up with quadrants here. In other words, a lot of times you take a rational function and you end up with a vertical asymptote there and a horizontal asymptote there, and that divides the thing up into 4 quadrants, and then you just have to figure out where to put your function. In other words, once I got it into 4 quadrants, I know a hyperbolic function is either going to look like this or perhaps like that. In other words, in quadrant 1 and 3. And in this kind of situation, it's pretty easy to figure out which. Just plug in a number for x and it'll tell you whether you're above the horizontal asymptote or below it or not.
Oh yeah, so that's pretty obvious.
Yeah, whenever you have strictly horizontal or vertical asymptotes, then it's not hard to figure out whether you're dealing with the red or the green. It's only when you have an oblique or slant asymptote that it's somewhat difficult, because I honestly didn't know whether it was the red or the green. But the one difference between the red and the green is the green has x-intercepts, the red doesn't have any. So if I can't solve this problem right here, it's got to be the red.
Mm-hmm.
Now, what is this point right? Whoops. What is this point right here? We don't know. And this point right there, we don't know. In other words, if I said to you, what's the domain? Well, the domain is negative infinity to 0 combined with 0 to positive infinity. So the domain is everything except the vertical asymptote, right?
Yeah.
But the range is negative infinity up to some value there, and then some value to positive infinity. And what are these? I can't tell from this function. I don't even have a way of calculating it. If they were to ever ask you that, it would have to be a problem that they were allowing you to put into your calculator. Once you get it into your calculator and you see this is what it looks like, now you can find local maximums and minimums by putting the trace on it. What kind of calculator do you have?
TI-84.
Perfect. You know how to use the trace to find maximums and minimums?
Yeah.
That's how you'd find that point. And you'd find both the x and the y value by doing that. And that's the only way to get it. I don't know of another way of getting it. Now, I could put it into Wolfram Alpha, and Wolfram Alpha probably shows it, the local maximums and minimums, but a lot of times I don't know if they do or not, to tell you the truth. Let's do another problem. Let's do one where the numerator is not exactly one higher than the denominator, just so we have a chance to do one of those.
X squared minus 1 over x squared plus 4.
Perfect. Hyperbolic in nature, because it's a quotient. Vertical asymptote, are there any?
Wouldn't it just be 1?
No. Remember, vertical asymptote you get when the denominator is 0. Can this denominator ever be 0?
Yeah.
No. You got x squared, which is always positive, and you're adding plus 4 to it.
Oh, so it's 2 positives, so it can't ever be.
Yeah, so that can never be 0, which means there's no vertical asymptote. None. How about horizontal asymptote?
1.
Correct. Y equals 1. Remember that asymptotes are always equations of lines. Well, I don't have any vertical asymptote. I have a horizontal asymptote at y equals 1. So my curve has to fit in that place there. Now, let's look at intercepts. In other words, the next thing to do once you've listed or drawn the vertical asymptote and the horizontal asymptote is to look for intercepts. Okay? Are there any x-intercepts? In other words, does this function cross the x-axis anywhere? And how do I figure it out?
Make y equal to 0.
Okay, so solve that. Remember, the only thing you care about is the numerator. Does not matter what the denominator is. The only way this thing's ever equal to 0 is if x squared minus 1 is equal to 0. So that's how you solve this. You can look at it as, okay, I'll multiply both sides by x squared plus 4. Okay, well then you have x squared minus 1 equals 0. Now,
and add 1.
Okay, I guess we could do it that way. I'm not a big fan of doing it this way. What's x equal to?
X equals plus or minus 1?
Yes. As long as you remember your plus or minus, this is a perfectly good way to do it. If you forget the plus or minus, then you're actually better off treating that as difference of perfect squares, and immediately you'll come up with the two answers, which are +1 and -1. That means those 2 points have to be on my curve. And I have a horizontal asymptote. Well, what happens when x is 0? In other words, let's figure out a y-intercept.
All right, so if x equals 0, it'll just be -1/4.
Okay, so this point right here is also on my curve. Now, I'm going to take a wild guess here, and I'm going to draw this curve. And notice why I'm drawing it this way. In other words, when you have asymptotes, the curve has to approach that. And in fact, the definition of horizontal asymptote is as x goes to infinity, what does the curve approach? Well, in this case, the curve approaches that horizontal asymptote that's at 1. Now, let me bring up Wolfram Alpha. Have I ever showed you Wolfram Alpha?
Yeah, you have.
I just want to do it real quick here because just as a verification of our curve. So it's x squared minus 1 quantity divided by the quantity x squared plus 4. Beauty of Wolfram Alpha, unlike your calculator, is it shows you what you put in. I didn't put it in right. I left out the 2 right there. Let's try it again. That's a sweet feature because that's a mistake that's hard to find on your calculator. Your calculator has so many parentheses you have to put in that it makes it very difficult to know whether you put it in correctly or not. Whereas Wolfram Alpha will always tell you what your input was. Okay? Now, it gives you 2 curves. One is merely zoomed in from the other. Okay? Notice that if I look at this bottom curve here and I put my axis, I'll have a horizontal asymptote at y equal 1. And it looks exactly like the way I drew it. The way I drew it is a little flatter, but that's hard to see on Wolfram Alpha. In other words, that's the correct curve right there. And the only thing we really needed were all of our asymptotes and our x-intercepts and our y-intercepts. And then we could do it. Okay. How about another one? And again, let's not use one that has a slant, just because I want to cover at least one that has a vertical and a horizontal asymptote, or maybe 2 vertical asymptotes.
I have to find.
You have one that's got 2 vertical asymptotes and 1 horizontal asymptote.
Would this be one? Oh no, that's way too many numbers.
Well, you would need 2 factors in the denominator. In other words, I can make one up. Let me give you one.
Okay.
Notice that you always want to factor these where you can. Now, what makes the denominator equal to 0? Those are your vertical asymptotes.
0.
What makes the denominator 0?
Equals. Wouldn't it just be -1? No, wait, no.
And positive 1.
Yeah.
In other words, x equal 1 and x equal -1. Either of those makes your denominator 0. Correct?
Mm-hmm.
Okay. Now if we go to draw this, I got a vertical asymptote there. I got another vertical asymptote there. Always where you want to start. How about horizontal asymptotes?
0.
It's the ratio of those coefficients.
Oh, so 1.
Y equal 1. So in this case, I don't have a grid that has 4 quadrants. I actually have 6 quadrants, okay? But I'm pretty sure what my curve is still hyperbolic in nature. In other words, my curve most likely looks like that and that, or could be in this quadrant and this quadrant, and I can quickly determine which. And then it does something in the middle that I don't know yet. First of all, let's figure out whether I have my black line or my red line. How can I easily do that?
X-intercepts.
Well, hold on a minute. Let's just, in other words, this is 1 right there, right?
Yep.
So if I plug in x equal 2, and I'm above this horizontal asymptote, then I'll know my black curve is correct. If I plug in x equal 2 and I'm below that horizontal asymptote, I'll know my red line is correct. Well, what's the function when x equal 2?
7 over, 7 over 1, so 7.
7/3. If I plug in 2 for x, this becomes 7, the numerator. If I plug in 2 down here, it becomes 3 in the denominator. Okay, so 7/3 when x is some value that's equal to 2, like right there, well, clearly I'm up there, right? I'm not on the red line. I'm above y equals 1. I'm at 7/3.
Mm-hmm.
So that tells me whether I'm the black function or the red function is correct. And so first thing let's do is get rid of this red. We know that's not correct. In other words, I know this part of my graph is correct. Now, the only thing I have to do is figure out what's going on in the middle. And typically there's only 2 ways that the middle behaves. It either does this, or maybe it does that. How can I tell which? And it's one of the 2.
Y-intercept.
Okay. What's the y-intercept?
So if you set it equal to 0,
Set x equal to 0.
it'd be 3, -3.
-3, which kind of looks like that. So I know that point is on the curve, but that still doesn't tell me the red is correct, because I could still have a black that does this. Right? In other words, just knowing the y-intercept doesn't solve the problem. What would solve the problem? What would tell me whether I was in the black or the red in here?
I don't know.
X-intercepts. Notice that my black line crosses the x-axis and it also crosses the horizontal asymptote, whereas my red line has no x-intercepts. So I want to set this whole thing equal to 0, meaning what?
So it would just be x squared plus 3 equals 0.
Does that have a solution?
It would be imaginary, so no.
So no. In other words, imaginary does not produce x-intercepts ever. So this tells me my red line is correct. In other words, the black line cannot be correct because there's no x-intercepts, at least not in between these 2 numbers here. In fact, this black line over here can't be correct either, can it? That shows an x-intercept right there. So another way these things can look, and this one almost certainly does look like this, is that way. Now, hold on a moment. In other words, that's the way my function's going to look. Now, here's one thing to kind of keep in mind that most of these things do. If I'm starting from the right and going left, well, that's headed to positive infinity, right?
Yeah.
If I go on the other side of the vertical asymptote, it's coming up from negative infinity. That's very, very typical. It's usually the opposite side when you get on the other side of the asymptote. Okay? Down here, I'm coming up from negative infinity. You're going down to negative infinity. So it makes perfect sense that that part of the graph would look like that.
Mm.
In other words, you can't always assume that it's in the upper right and the lower left, or the upper left and the lower right. These functions, these rational functions, can take all manner of shape. And since I have Wolfram Alpha pulled up, let me put it in there real quick. It was x squared plus 3 divided by x squared minus 1. X squared plus 3. No wonder it's taking so long.
Oh.
Yeah, I had x squared plus 231. Okay, so that's my function, and this is what it looks like. And we were able to figure all of that out merely by knowing vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts, and that's all it took.
Mm-hmm.
But a key part of that is not only do you have to know if you have x and y intercepts, but it's helpful to plug in numbers to the right, sometimes in the middle, sometimes to the left of your vertical asymptotes, because that helps you spot this. In other words, let's say I wasn't 100% positive about this one on the upper left here, my graph. Well, I'll plug in x equal minus 2, right? Well, when x equals minus 2, I end up with 7 in the numerator and 3 in the denominator. So that point has to be on my curve. And in fact, I can see from this function that that's an even function. It's not odd, it's even. And I don't know if you've had even and odd functions or not, but even functions are symmetrical about the y-axis. So this curve we drew is perfectly symmetrical about the y-axis, as it could be because it's an even function. Do you know even and odd functions?
No, I don't know about odd functions.
Well, let's just talk about them in our last minute here. A function is even if f of minus x is equal to f of x. A function is odd if f of minus x equals minus f of x. Notice that if I plug in minus x for x here, I get the same answer, right? I get x squared plus 3 over x squared minus 1. So this is a true statement, which makes it even, and even functions are always symmetrical with the y-axis, Odd functions are not symmetrical with the x-axis, they're symmetrical with the origin. In other words, an odd function is this one right here. Has symmetry with the origin. And what symmetry with the origin means is if I flip it over the y and then flip it over the x, that's what I have. Well, this function here, f of minus x, ends up being minus x cubed, which is the same as minus f of x. So as long as f of minus x is equal to minus f of x, you have an odd function and you're going to be symmetrical with the origin. And that was actually very helpful on the previous problem. I wouldn't have made my original mistake if I'd have noticed that. In other words, I never would have drawn it in the upper right and the lower left quadrants. I would have made it symmetrical. So all I needed to do was figure out how it looked to the right of the y-axis, reflect it. It's going to look exactly that reflection of that to the left of the y-axis.
Mm-hmm.
All right. Now, when we started, you said, can we do all of these? I don't know, did that mean, do you want to go longer than a half hour, or did that mean in the half hour that we were going to do?
Oh, yeah, that in the half hour.
Okay. So
I covered pretty much everything now, so thank you.
You're good to go now? Okay.
Yeah.
One last thing. If I had this, the way I find my, this one's not so easy to find the slant asymptote, right? We know that it's going to be oblique because the numerator is exactly 1 power greater than the denominator. The way you get it is you have to do the long division. You have to do it this way. And you have to put in a dummy variable in there. Okay? Whatever you get, the linear term plus some remainder, you don't care about the remainder, you can cross that off. But whatever this is the equation, and in this case it's x, but there might be another number involved with it. But whatever this linear term right there, that's the equation of your slant asymptote.
Okay.
In the one problem we did, we only had a single denominator of x, so it was actually easier to just separate it into two fractions. But the typical way you find the equation of a slant asymptote is by doing the long division and throwing away or not really caring about your remainder.
Okay.
Okay? All right, Jake, I'll let you go.
Good, thank you.
You're welcome. I'll talk to you next time. Oh, before you go, 1 second. Your mom said that Monday was not going to work for you on a regular basis. She wondered whether Tuesday would work for me. And at first it didn't, but it looks like I'm going to have a regular spot at 5:30 on Tuesdays. You want me to move you into that?
Yes, please.
Okay, I'll do that. And so next week, it'll be Tuesday at 5:30 and not Monday.
Okay, sounds good.
All right, talk to you next Tuesday.
All right, thanks.
You're welcome. Bye-bye.
Bye.